Hello and welcome to this video where we're going to be looking at the energy for combined science past paper questions. What I suggest you do is download this booklet from the link, it's in the description below, and have a go at those questions. When you've completed them, come back here, go through your answers as we do to see how well you've done. So let's get started with question 1. Here we go. So in question 1, a student is using an electric motor to lift a load. In the motor, the electrical energy is transferred into other types of energy. Some of this is useful and the rest is wasted. Name the useful energy output from the electric motor. Well, electric motors always transfer electrical energy to kinetic energy. So kinetic energy is our useful energy output, and that's because it's going to move the load up. What eventually happens to the wasted energy? When these questions are always the same, the wasted energy is always dissipated into the surrounding environment as heat. Okay, question 3. The graph shows the input energy that the motor needs to lift different loads by 1 metre. What can you conclude from the graph about the relationship between the load lifted and the input energy needed? Well, firstly, we can see here that as the load in newtons increases, the input energy increases. So that's our first marking point. As the load increases, the input energy increases. Now, I'd always suggest using the axes labels here when in your answer. It gives you a much better answer. Now, obviously, we need a second point. Now, what's obvious about this graph, it's not a straight line increase, it's a curve, which starts off gradually and then increases rapidly. So we can say that that increase is slow for small loads and then increases rapidly as the load increases. And we can see this in the graph. We've got a very shallow curve and the gradient gets steeper and steeper and steeper as we move up the graph. So looking at question 2. Question 2 shows a battery operated remote control car. It tells us that the car's battery contains a store of energy, and as the car moves, energy from one store is transferred to another store. Describe how the different stores of energy change as the car moves. So the first store of energy is the car's battery, and that would be chemical energy. So the chemical energy in the battery will decrease, and that's because it's getting transferred as kinetic energy, and then eventually the store that it'll end up in will be the internal energy of the surroundings, which will correspondingly increase as our chemical energy is decreasing. The car has a top speed of 12 meters per second and mass of 800 grams. Write down the equation that links kinetic energy, mass and speed. So this is just learning your equations. So kinetic energy equals a half multiplied by mass multiplied by the velocity, or the speed squared. Okay, calculate the maximum kinetic energy of the car. So we can use the equation from above. So it's a half multiplied by the mass. The mass here is 800 grams. We want to turn it into standard units of kilograms, which is divided by 1,000, which gives us 0.8, multiplied by the speed, which is 12, not forgetting squared, and if we work that out, that's going to give us 57.6 joules. Explain why having a more efficient motor increases the top speed of the car. Well, a more efficient motor will mean that we'll have lower proportions of that energy as waste energy. So lower proportions of energy wasted, and therefore the higher proportion will be in the useful energy, which in this case is making the remote control car move, which will be the kinetic energy. So higher proportion of energy converted to kinetic energy. Okay, let's have a look at this bottom question here. So 2.5. A driver wants to buy a new car. They're considering whether to buy an electric car or a petrol engine. The table below gives some data about the electric car and the petrol car. Which car would be the most economic over its 12-year lifetime? Use data from the table to support your answer. We should include the cost difference in our answer. So if I was doing this, I would want to think about the two cars separately. So we've got the electric car, we've got the petrol car. So the electric car is going to cost £27,000 plus £250 multiplied by 12, because it's £250 per year and we're going to be using it for its 12-year lifetime. So if we work that out, we're going to get £30,000, and we can do the same for the petrol car. So the petrol car is cheaper to buy at the start, so it's £15,000, but it's going to cost us £2,000 every year, and if we work the total of that out, it comes to £39,000. So we can clearly compare the differences, which is 9,000. 39,000 minus the 30,000 is £9,000 cheaper or more expensive, which way you think about it. So the electric car is cheaper because it will be £9,000 less cost over the 12 years compared to the petrol car. So we could turn that into our answer. Okay, let's have a look at question number 3. So in question number 3, the miners are working in a salt mine. They're using a smooth wooden slide to move quickly from one level to another. And it tells us that a miner of mass 90 kg travels down the slide. Calculate the change in gravitational potential energy when he moves 15 metres vertically downwards, and it gives us the gravitational field strength here. So we know that the gravitational potential energy equals the mass times the gravitational field strength times the height. So our mass is 90, already in standard units. Our gravitational field strength, it's given to us here, is 10. If it wasn't 10, we'd use 9.8. And the height of the vertical drop is 15 metres. So if we work those out, we're going to get 13,500 joules. Okay, calculate the maximum possible speed that the miner could reach at the bottom of the slide. Show clearly how you work out your answer and give your answer to 3 significant figures. So what we're using in the premise of this is that when the miner starts off, they'll have their maximum GPE, and by the end they'll have lost all of that GPE and it'll have all been converted into kinetic energy. In reality, that obviously wouldn't happen, and we'll look at that in the next question. But for the moment, we're going to assume that the GPE equals the kinetic energy. We know that our equation for kinetic energy is half mass times velocity squared, and so we can start to plug those numbers in. So the kinetic energy, if we're assuming is the same as the GPE, the maximum will be 13,500 equals a half times the mass, which we can take from here, which was 90, multiplied by the velocity squared, which is what we're trying to work out. So if we bring these over here, so divide by half and divide by 90, we end up with 300 equals v squared, and therefore to calculate v, we would do the square root of 300, which will give us 17.32051. And then finally, they want us to give it to 3 significant figures. So there's our first significant figure, our second, and our third. So 17 point. Look at the next number. It's not a 5 or more. So this will stay at 17.3. Okay, so the speed at the miner at the bottom of the slide is much less than calculated. Explain why. Well, this is because as the miner is sliding down, work is therefore being done against friction. And this is because the slide isn't perfectly smooth, or the clothes of the miner as they slide down isn't perfectly smooth, which will need to be overcome. So some of that kinetic energy will actually be transferred to the surrounding air as thermal energy. And there we go, let's move on. So here we have question 4. In this one, a student is investigating a specific heat capacity of 5 different metal cylinders, each metal cylinder having a mass of 2 kilograms. They use an immersion heater and they transfer 18,000 joules of energy to each of those different metal cylinders. And you can see the setup there. And they're measuring the temperature of the metal cylinder at the start and at the end of each experiment using a thermometer. And then they can use that to calculate the temperature rise, which you can see on the graph. So firstly, we need to suggest an approximate resolution for the thermometer used in the investigation. When we have a look at these numbers here, we can see that this is 10, what have we got there, 23, 20, so all of those are given to the nearest 1 degree Celsius. So I suggested the approximate resolution that they used was 1 degree Celsius, and the reason for that is temperatures all seem to be recorded to the nearest 1 degree Celsius. Okay, the mass of the metal and the energy transferred to each metal were control variables, so just another variable that could have been controlled. There's a whole range of things that you could put here. One that stands out to me is the room temperature. You'd want that to be the same in all of these things. Also, we can think about the insulation in the picture here. So the insulation would need to be the same. And we need to say exactly what that would be, so the type of the insulation or the thickness. I'm sure there are others. 4.3, which metal has the highest specific heat capacity? Give the reason for your answer. So the highest specific heat capacity in this case will be the aluminium. And the reason is because it's got the smallest temperature rise. And then finally we need to calculate the specific heat capacity of the steel using the results of this investigation. So for this one we're going to use the equation that energy transferred equals the mass multiplied by the specific heat capacity multiplied by the temperature change. So if we look at those numbers, we're doing it for the steel. The steel is over here. So we can see that the steel is coming in just 1 below the 20. There's 5 of the marker points between 10 and 20, so each one represents 2. So therefore we know that the temperature change was 18. The specific heat capacity I'm going to leave as S. We don't know what that is. The mass over here, it tells us earlier on the question is 2 kilograms. You can see that at the top here. And the energy transferred for this one again was given to us at the start of the question, which was 18,000 joules. So we get an equation that looks like this one over here. We then want to rearrange by bringing the 2 and the 18 over here, so we get 18,000 divided by 2 times 18 equals S, and if we work that out we get 500. Again we need to give the units. Well, the units are given to us here. So this 18,000 was joules divided by 2, which was kilograms, multiplied by 18, which was degrees Celsius. So there's our units, joules per kilogram degrees Celsius. Let's move on to question number 5. Okay, in question number 5 we're looking at a farmer who's installed a biogas electricity generator on their farm. The device generates electricity by burning the methane that's produced from the rotting animal waste. Methane is a greenhouse gas, and when the methane burns, carbon dioxide and water are produced. The animal waste rots in an anaerobic digester. The digester and the generator are kept inside a farm building and can't be seen from the outside. The animal waste using the anaerobic digester is a renewable energy source. What is meant by an energy source being renewable? So again, check out our knowledge builders to remember the answer to all of these questions. It's just recall. So a renewable energy source is a resource that can be replenished faster than it is being used. It's just one reason why farmers have been encouraged to install their own biogas generators. So there's many things that you could think about here. It reduces demand on the national grid. If they're producing their own energy source, then obviously they're not needing to take it from the national grid. Okay, the farmer's monthly electricity bill using the mains electricity bulb was £300. The biogenerator cost the farmer £18,000 to buy and install. Assuming the biogas generator provides all of the farmer's electricity, what is the payback time for the generator? So here it's going to cost them £18,000 to install, and their monthly electricity bill is £300. So therefore we want to find out how many months of payment it takes to go into that £18,000. So if we divide the 18,000 by the 300, it gives us 60 months. So in 60 months time, they'll have saved enough £300 to outlay the cost that they've done there. So our answer there would be 60 months or 5 years. It would have been cheaper for the farmer to have bought and installed a small wind turbine. Give two advantages of using the biogas generator rather than a wind turbine to generate the electricity used on the farm. Well, the advantage with these questions is that we're given the clues in the text. So for example, you can see here that it says that the generator kept inside a farm building and cannot be seen from the outside. Obviously a wind turbine would need to be out in the open to catch the wind, so we could use one of the advantages is that they are not an eyesore. The second one as well, we could look here, it tells us that they can use the rotting animal waste. So one of those other advantages would be that it uses up their waste material. Of course, there's plenty of other options. You could talk about the fact that it's much more reliable. Obviously, wind turbines only working if the wind is actually moving. Let's move on to question 6. In question 6, we've got a diagram which shows two switches on a room heater. The heater has 3 power settings, low, medium and high, and as you can see it's given us the power for 2 of them. So when both the switches are on, the heater works at the highest power setting. What is the power of the heater in kilowatts when it's switched to the high power? So it says in high power they're going to be, both of these will be on, so it will have 700 plus 1400, which equals 2100 watts. It wants us to give the power in kilowatts, so to turn watts into kilowatts, we're going to divide by 1000. So divided by 1000 will give us 2.1. The heater is used on the high power setting. It's switched on for 1.5 hours. Calculate the energy transfer from the mains to the heater during that time. Show clearly how you work out your answer and give the unit. So we're going to use the equation energy transferred equals power multiplied by time. So we want to know the power, which we've just got here, which is 2.1 kilowatts, but we obviously want that now back in watts as our standard units, multiplied by the time. So the time is 1.5 hours, but we want that eventually in seconds. So we'll first convert to minutes, multiply it by 60, and then we'll do the same again to turn it into seconds. So that will give us 90 minutes, which is 5,400 seconds. So we're going to get quite a large number here, which will be 11,340,000. It's not giving us a unit, so it's energy transferred, so it'll be joules. So moving on, just a quick one on elastic potential energy. How much elastic potential energy does a spring store when it's compressed by 0.2 meters if it has a spring constant of 5 newtons per meter? So the elastic potential energy equals a half multiplied by the spring constant multiplied by the extension squared. So it will be 0.5 multiplied by the spring constant is 5 multiplied by the extension. It doesn't matter if it's an extension or compression, it's the same number. So we use 0.2 as it's in meters and meters here, not forgetting to square it. If we work that answer out, it gives us 0.1 joules. Okay, let's move on to question number 8. In this question, we're looking at a roller coaster. The roller coaster car is raised a vertical distance of 35 meters to point A. Just label that on so that we remember. And that takes 45 seconds. The mass of the roller coaster is 600 kilograms and the power rating is 8,000 watts. So we need to calculate the percentage efficiency of the motor, and it gives us the gravitational field strength. So firstly, we want to work out the gravitational potential energy that is gained, which is the mass times the gravitational field strength multiplied by the height. So the mass is 600 kilograms multiplied by the gravitational field strength, which is 9.8, multiplied by the height, which is 35, and if we do that we get 205,800 joules. Now we want to work out the percentage efficiency of the motor. So it says the motor has a power rating of 8,000 watts, but we want to see what it's actually giving. So we're going to use power equals energy transferred divided by time. So energy transferred we just did was 205,800 divided by the time, which was 45 seconds. And if we work that out, it gives us 4,573.3 watts. So we can see that it's quite clearly not giving us the same watts as the power rating. So to work out the percentage, we would do the 4,573.3 divided by the 8,000 multiplied by 100. And if we work that out, it gives us an efficiency of 57.17%. Okay, the roller coaster rolls from point A to point B, a drop of 35 meters. Calculate the speed of the roller coaster at point B. We're assuming that the decrease in potential energy is equal to the increase in kinetic energy store. So what we're assuming, therefore, is the amount of GP it has at A is equivalent to the amount of kinetic energy it has at B. So we've already worked that out previously. We've got the number here. So we're going to say that the GP equals the kinetic energy. So therefore we know that the kinetic energy equals a half mass times velocity squared. So the kinetic energy equaling the GP will be 205,800, the number from here, equals 0.5 multiplied by the mass. The mass is 600 kilograms multiplied by V squared. So we're going to bring these over by dividing, so 205,800 divided by 0.5 times 600, which is 300, equals V squared. Working that out gives us that 686 equals V squared. So to work out V, we're going to square root 686 to give us V, which gives us an answer of 26.2 meters per second. Let's move on to question number 9. So this question's looking at a swimming pool. It tells us that the sun transfers energy to the swimming pool, gives us the mass of the water in the swimming pool and the specific heat capacity, and we need to calculate how much energy needs to be supplied to increase the water temperature by 5 degrees Celsius. So we're going to use the equation energy transferred equals mass times specific heat capacity times temperature change. Energy transfer equals the mass, which is 5,000 from here, multiplied by the specific heat capacity, 4,200, multiplied by the temperature change, which is 5, and if we work that out, it gives us 105 million, and our unit for energy, as always, is joules. The sun supplies the energy to the water in the pool at a rate of 16 kilojoules every second. Calculate how much time it would take for the energy from the sun to raise the water temperature by 5 degrees Celsius. So it gives us 16 kilojoules. We're going to work this question out in joules. So to convert, we times it by 1,000, which obviously gives us 16,000 joules. Now we know it's going to take 105 million joules to heat the water. So we want to find out how long it will take to do it just using the sun. So we're going to divide that by the 16,000, and if we work that out, we're going to get 6,562.5 seconds. So we'll just round our number to the nearest whole second. On one day, the temperature of the pool is 7 degrees Celsius lower than the air temperature. The time it takes for the pool temperature to rise by 5 degrees is less than this answer. Suggest a reason why. Well, that's because in this answer here, it's just taking the energy from the sun. Obviously, if the temperature of the pool is 7 degrees Celsius lower than the air temperature, then some of that thermal energy from the air is also going to heat the pool up, as well as the energy from the sun. So we can say that it will gain energy from the air or the surroundings, which will make it therefore faster. Yeah, we're whizzing through loads of questions. Let's keep going on with question number 10. In question number 10, we're looking at this diagram of the cavity wall insulation being installed in the wall of a house. So we've got the two layers of the house, 2 bricks and this gap inside, and this person is pumping in insulation into that gap in between. Explain how the hut wall reduces the unwanted energy transfers. So number 1, we can talk about the layers. So the wall now has 3 layers because you've got the inner wall, the insulation, and then the outer wall. The cavity wall will have a low thermal conductivity because it's not going to allow the energy to transfer through it very easily, and therefore will have less energy transferred by conduction. In the next one, it tells us that the cavity insulation was tested, the heating inside the house was switched off, and then the temperature was measured every 20 minutes for 2 hours, and this table shows the results. So you can see obviously the temperature dropping as the wasn't being heated anymore. Determine the temperature inside the house after 30 minutes. So you can see that we've got 20 minutes and we've got 40 minutes, but 30 minutes would be somewhere in between. So we're going to make the assumption that these look like they're going down roughly equally. So we're going to assume that 30 would be somewhere halfway between the two. So it started off at 20.8 and to 17.4. And we work out the difference, so divide it by 2, that gives us 1.7. So we know it's roughly 1.7 in the middle of those. So let's do 20.8 and it will lose 1.7 degrees. And if we do that, it will give us 19.1 degrees Celsius. So this figure shows how the gas boiler could be used to heat the house, describe how different energy stores are changed by the boiler. So the fuel will have chemical energy, and that will be decreased. This will then heat the water, so the thermal energy store of the water will therefore increase, and that energy will therefore get transferred to the air in the house, the surroundings, so the thermal energy of the air will also increase. Okay, so this last one, to heat the house, the boiler transfers 15 megajoules of energy in 10 minutes. Calculate the power of the boiler. So for this one, we're going to use the equation power equals energy transfer divided by time. The trick with this one is that we haven't got standard units for either of our values. So we want to convert 15 megajoules into joules. And to do that, we're going to times by 1,000,000. So that will give us 15 million joules divided by the time. And again, it's in 10 minutes and we want it in seconds. So we're going to times it by 60, which will give us 600. And if we do 15 million divided by 600, we get 25,000 watts. On to our penultimate question, number 11. This one's looking at a wind turbine. So a particular wind speed, a volume of 2.4 times 10 to the 4 meters cubed of air, passes the blades each second. The density of the air is 1.2 kilograms per meter cube. Calculate the mass of air passing the blades per second. So the first thing we want to do is use our equation density equals mass divided by volume. We're going to want to rearrange this because we want to find the mass. So we're going to bring the volume up by multiplying, so density times volume equals mass. The density of the air is 1.2 multiplied by the volume, which is here, 2.4 times 10 to the 4, will give us our mass. And if we work that out on our calculator, we get 28,800 kilograms. The power output of the turbine is directly proportional to the kinetic energy of the air passing the blades each second. Describe the effect on the power output when the wind speed is halved. Okay, so it's a bit of a tricky one here. It's going to rely on us knowing the equation kinetic energy equals half mass times velocity squared. So let's think what's going to happen here. So if the wind speed is halved, the mass of air passing by is going to be halved as well. So this is going to divide by 2, and therefore that will reduce the kinetic energy by half. Secondly, if the wind speed is halved, that's also going to change the velocity down by half. But because it's squared, it's actually going to change it down by 4 times, as 2 squared is 4. So overall the kinetic energy is going to be halved and then quartered, so the overall effect by that is actually going to get 8 times smaller. So if we were writing this, we would say that the mass will halve, which will bring the kinetic energy down by 2, the velocity will halve, which will bring the kinetic energy down by 4 times, and the combination of those is 8 times smaller. At a different wind speed, the wind turbine has a power of 388 kilowatts. The mass of air passing the wind turbine each second is 13,800 kilograms. Calculate the speed of the air passing the blades each second. We're going to assume that the process is 100% efficient. So firstly, let's just change this into our standard units. So 388 kilowatts into watts. We're going to times it by 1,000, which will give us 388,000 watts. We're going to assume the process is 100% efficient, so therefore we're going to assume that all of that energy will be transferred. So we're going to put that into our kinetic energy equation. So 388,000 equals a half, multiplied by the mass, 13,800, multiplied by velocity squared. We now want to rearrange this, so we're going to bring the half times the 13,800 over here to give us v squared, and if we work that out, that gives us 56.23, which therefore we want to square root to give us v, which is 7.4987, which gives us a speed of air of 7.5 meters per second. If they're trying to do the trickier questions, it's always velocity that they want you to calculate, like we've done here. And then our final question is question number 12. Now if you've got this far, you'll notice that question 12 is exactly the same as question 2, so it should make it nice and simple to check over your answers. So hopefully that's helped you with your exam technique and answering those questions. The more practice that you can do, the better, and the more prepared that you'll be for your exam. If you haven't managed to download those questions, the link is in the description below, so make sure that you do. Check out our other videos and make sure you subscribe. And as always, happy sciencing!